On the other hand, in a divergent channel, the boundary layer becomes thicker with a corresponding decrease in wall shear stress. In this case, we have an unfavorable pressure gradient. The increasing pressure associated with a decreasing mainstream velocity decreases the velocity in the boundary layer, so velocity gradients and shear stress are less, and the boundary layer is thicker. At a larger angle, the decrease in velocity is so great that somewhere along the wall, the velocity gradient normal to it becomes zero, accompanied by a local reversal of flow immediately downstream of the point. The fluid, which was in the upstream boundary layer, is no longer in contact with the wall and is separated from it by a region of reversed or recirculating flow. The boundary layer is said to have separated. Point on the wall where the fluid in the upstream boundary layer meets the fluid from the region of flow reversal is called the separation point. The wall shear stress is zero there. Here, the point of separation of the laminar boundary layer is near the first wire. The boundary layers we have seen so far have all been laminar. However, in most practical high Reynolds number situations, the boundary layers are not laminar. Rather, they are turbulent. Flow along a cylinder filmed with a high-speed camera can show the stages in the transition of the boundary layer from a laminar one to a turbulent one. A slight adverse pressure gradient causes transition to occur within the field of view. The steps in the transition are very complicated and interdependent. First, there is a growth of nearly two-dimensional waves, the Thomaine-Schlichting wave, followed by the appearance and growth of three-dimensional disturbances associated with streamwise vorticity. Then turbulent spots can be seen. And finally, fully turbulent flow appears. Here, the exact position where growth of two-dimensional disturbances begins depends on random small-scale fluctuations in the flow, and therefore varies with time in a random way. This boundary layer around a channel bend is made turbulent by placing an obstruction in the layer upstream. The obstruction stimulates the naturally occurring processes and hastens the onset of transition. The flow here is all downstream. Removing the trip rod results in separation and backflow. Bubbles accumulate at the separation point. In this diffuser, which was used before, we have made the bottom boundary layer turbulent by inserting a trip rod upstream. The turbulent boundary layer is able to withstand the adverse pressure gradient in the diffuser, while the laminar layer along the top wall is separated, allowing reverse flow. These timelines show that in the turbulent boundary layer, there is no separation. Overall flow is downstream. To see